talk about like something related to tropicalization map, which helps us to define the motivic volume for define like a volume functor from varieties over field K, where K equals the K over here. I choose it to be like the field like of the, I don't know how to say that, the pixel series, pixel series. Yeah, like the, yeah. So it's algebraic closed, and my K over here is an algebraic. Yeah. So I am gonna like, so this field has a valuation, like it's a valued field. Like there exists a map from like an element here goes to like the rational numbers. And yeah, and I am gonna consider like T to be a algebraic torus with dimension n, and it is over this field. And so it is the spec K of like the big K of x1 plus minus 1 da 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 xn plus minus 1. And I will have a subvariety of T, which is this x, a closed subvariety. And I will tell you something like a general way that is used in the inNicaise-Payne paper to define a volume for any like closed-up varieties of this form. And actually, they do it for like the semi-algebraic, like any semi-algebraic subset of any like subvarieties. And yeah, so this is like the basic setting. So there exists so suppose we have like a field like this and we have a subvariety like this. There exists a tropicalization map going from X to the lattice, like Q to the N, where I will use NQ. And this is simply by taking each point and I map it to the value, like under this like the value of this field of X. Okay. And like probably in 5 minutes, I'm gonna give you like an equivalent definition of the tropicalization, and we will actually like use both definitions throughout the talk. Okay, so yeah, so first I am gonna tell you something called the initial degeneration. So as I said last time, like a tropicalization process is like we are actually like taking some degeneration or a degeneration of this X under some families, and the tropicalization sort of tells us like how the central fiber is gonna look like combinatorial, like the combinatorial structure of that. So the initial degeneration is an example of this. And so suppose we start with some element inside this co-character lattice of T. And the idea is associated to each such omega, there we can construct a partial compactification of T, which I call it T omega. And this initial degeneration is so this is a partial compactification of T. So which means there exists a piece of X inside this T omega, and we can take the compactification, like the closure of X inside this T omega, and the initial degeneration is gonna be the central fiber of X upper bar inside this compactification. So let me give like the precise definition. So right now I start with the data omega, and I choose, I construct a ring out of this omega, which this ring is a subring of like the big field of M. M is the character lattice. Character lattice of the torus. And be the collection of the polynomials such that it satisfies the if we write it as summation ai x to the ui such that if I pair this ui with omega, then plus the value of ai, it is larger or equal to 0. Yeah, so we can sort of think of this as, because if you look at this, this is similar to like if you have a toric variety and if you have a cone of it, and then you are taking like like you are using that as cone picture to construct the toric variety. So it is similar to this idea, but over here we simply pick one direction. That is like we only compactify in that one direction. And so let me give an example. So so if we have this, like one of the observation is that if I base change it to spec of K, like the big field over here, it is gonna isomorphic to the K of M, which means the generic fiber is the torus. Is torus T. And for the central fiber, it's gonna be like different based on the omega you choose. Yeah. So and like I forgot to mention, like this. Yes. Oh yeah. Thanks. Yeah, and this partial compactification d omega here is defined to be spec of R M omega. So this is the definition of that function, partial compactification. And the generic fiber is the algebraic torus. And and we define the initial degeneration to be the central fiber over the spec K, spec small k. And let me give an example just to see how this works. So I calculate this myself, so I'm not 100% sure if it's correct. Yeah, so maybe like we can check together. So suppose my T is GM squared, and I just pick a subvariety like T squared X plus T squared Y equal 0 over here. And I pick an omega to be like 1, 0. So if we check this, like this polynomial is gonna be so over here I like when I pick like ui to be something like 1 something, so like x, it is allowed to I have like t to the minus 1. So this ring is gonna be x t to the minus 1 t x minus 1 and probably y plus minus 1. Yeah. And so if I am looking at this initial degeneration over here, and so initial degeneration will be like the compactification of x inside Yes. Yeah, sorry. I think I did this wrong. This is the compactification of M inside the T omega. Oh, yeah, sorry. Wait. Yes. Wait, no, here is R. Yep. Yeah, sorry about. Yeah. Yeah, so in this case it's just the base to so it's the base change to the spec smart k. Because it's like
Wait, this one. Yeah, it is all family.
yeah. 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 Yeah, that's right. So if you see it over here when t does not equal to 0, it's like like this thing give us something like x plus y equals 0. And if you are, but like when you look at the compactification of this thing inside the inside of t omega, what you get is something like ut plus y equals 0, where my u over here is xt to the inverse. So when I take t equals 0, the special fiber I get is y equals 0, which is actually not a limit over here, which means in this case the initial degeneration is empty. Yeah, I did not actually like tell you like, yeah, let's try to go through. So over here we take omega equals 1, 0. And so I am using the definition. I look at like the collection of the elements here. So I get xt minus 1, and the generators are xt minus 1, t minus 1, and y plus minus 1. And so right now I want to construct the xw to be the closure of x inside this big thing. And over like t does not equal 0, like this part is the same as like the function defined by x plus y equals 0. And when like I go to the point t equals 0, when I quotient out t, like I know this thing is quotient out. So if you are looking at the whole family over like the central fiber, it's actually like k, it's actually generated by k t minus 1 and y plus minus 1. So it's actually an A1 cross GM. Yeah. And if you rewrite this equation in terms of, like you take the compactification, you write this equation, it becomes ut plus y equals 0. And yeah, and like this t gets cancelled out because you are looking at the central fiber, where this is t equals 0. So the equation for, like, if you are gonna compactify it, then it's gonna be y equals 0. But this limit does not exist. Yeah, exactly. That's the point. Yeah, so this is an example where the initial degeneration is empty. And yeah, and I had like another example where you can go check and like compute it by yourself if you take w or like omega equals minus one. In this case, there like the initial degeneration is actually not empty and it's an A1. Like, yeah. And there's a yeah over here. Yeah, so this is like I think it's the Sternfeld's tropicalization definition, is that suppose like uh suppose the initial degeneration is not empty, then this omega lies in the tropicalization of X. Yeah, so the alternative definition. equation of tropicalization of X are the points that the initial degeneration is content. Okay, so next I am gonna tell you like the definition of a Schön variety. I hope I'm pronouncing it correct. Like Schön. A sub-variety of the torus to the k to the n are those acts such that its initial degeneration is smooth for all omega. Yeah. So the fundamental theorem of tropical geometry tells us such like the tropicalization of X is a polyhedral complex. And we can write it as like the unions of cells of different like dimensions, and we can organize them like write like a polyhedral in like as the unions of the polyhedrals. And so if we pick a cell and if we take the inverse image of the interior of this, intersect it with X. So X intersect trop of like the interior of this cell. So this, and if we go over, this gives us like a sub-variety of X. And if we go over all of the like the polyhedrons or like the cells of tropicalization of X, it actually gives us a decomposition of X in terms of the disjoint unions of all of the things of this form. So I think in the motivic volume paper, that their first result is that like for these kind of things, we know how to define the motivic volume of it, and the volume is defined to be the volume of this volume of this equals -1 to the dimension of gamma times the initial degeneration of omega of X, where omega is an element inside the interior of gamma. And it does not matter which omega we choose for this, because they are all give us like the isomorphic varieties as the initial degeneration. So this is the first result that they used in like define the motivic volume. And but unfortunately, I don't like they use the like the Hofschuski, like the semi-algebraic, like that motivic integration technique, which I do not understand. And hopefully next time, Eric or like you can like explain this part. Yeah, yeah. So this map is like from K varieties, like the gross integrating of the like the K varieties to the gross integrating of the small K varieties.
Oh, okay.
Yeah. Yeah, this is like their definition, like the. Yes, yeah. So this part actually comes from Euler character. It's called bounded Euler characteristic on NQ on the lattice. So their tropical Fubinis theorem actually relates like the. Yeah. Basically, it's saying like this tropicalization map. Like the push forward of it, this like when you take the integration is the one that you get by taking the volume.
So the volume is like latitude.
Yeah, yeah, additive, like based on like by the disjoint union. So over here you gave a decomposition.
So the equation is like for varieties of this. Oh, I got it. Yeah. So this is like for non-Archimedean.
Yeah, but your K, this K can be C. Yeah, but this one is defined. This one I actually simplified a little bit because this one I used the algebraic closure of that, like the pixel series, but they generalize it to the case where this is the like the power series, like the without the algebraic closure of this. Yeah, how do you say it? Like the Laurent powers? Yeah, Laurent series. Yeah, so they generalize, like in their paper they generalize it to. Yeah, they work out the like the Galois action, like the thing.
Yeah, actually, basically, what I do with those theories is really have to only work over some, some cyclic cover.
Yeah, so let me tell you what is the like the tropical Fubinis theorem of it, and maybe before that, let me tell you like about this bounded Euler characteristic on the on the lattice over here. So yeah, so a constructible set and Q is a finite Boolean combination of polyhedron. And the bounded Euler characteristic assigns one for each non-empty polyhedron. So one of the examples that such Euler characteristics vanish are like the ones that you have half line. So yeah, so it will be like you have a polyhedron. This is one, and you minus a point, and the point also has. Oh yeah, because it's like Boolean. So it's plus.
Yeah, I've just done about this characteristic size one.
Yeah, and yeah, so the thing. Yeah, so if it's like a half line, and we can write it as like an interval minus a point.
Okay.
Yeah. So there's plus minus. So it's 1 minus 1. So it's yeah. And in one of the like results that they proved is that suppose you have like the tropical like cell like this, and the Euler characteristic of this thing equals -1 to the dimension of this cell. And if given like this cell is bounded, and this Euler characteristic equals 0 if this cell is not bounded. Yeah, if it's the interior of this cell. So yeah, it's a theorem, like they proved. Yeah, so it's a result. It's a result, and I think one of the example that we can see is that suppose this is a point, then this is a one -1 to dimension of a point. If this is like an open, because it's the interior of this thing, so it's -1. Yeah. Yeah, and now I can claim like the tropical Fubinis theorem is that suppose we are given the like this tropicalization from T to NQ, and the theorem states that I can construct a push forward of the like the index functor for this x. This map is a constructible function. And the volume of x is the integration over this NQ of this push forward with this Euler characteristic. This bounded Euler characteristic. Yeah. So for this tropical push forward,
just the characteristic function.
yeah, of x. X is a subvariety of t. Yeah, and this function, let me think. So it's this function should gives you a map from NQ to the gross integrating of the small k varieties. Such that for each omega inside over here, it will gives you the fiber over this thing. So it's x. So it will give you the volume of trop inverse of omega intersect with x. Let me double check if I'm saying it correct. Because
So what's the correct?
Sorry, can you say that again? Oh, yeah. So it's basically, so if you do not have this, then like if it's one NQ, then it's simply like the trop inverse of omega, and this one x gives you the part that you intersected with omega, like you intersected with x. Yeah. So yeah, but let me make sure I am not lying over here. Oh. Yeah, but I don't think this is the one that. Yeah, so here they gave like a Fubinis theorem statement for the case, which is a simpler, like case that is slightly simpler than this, where we will also mention it afterwards. So I will just say it now. So suppose you have another torus. So suppose you have a map from one torus to another torus, and you have the tropicalization like NQ to NQ prime over here, and so there. So this is another like the tropicalization map, and if you have so let's see. So if you have so there exists a type of morphism which are called monomial morphisms, which are basically the morphisms such that if you are given this thing and this is an affine linear map, and this whole thing is like commutative. And so suppose right now I have an Euler characteristic on here, and another like if I have a constructible function from this n of Q to some abelian group A, which I'll name it F, and the Fubinis theorem basically tells you that so this push forward is gonna be a map from NQ prime to A, where it's the thing we did, which is the integration of over like the inverse of and the Fubinis theorem is that Q of prime equals so let me unwrap the thing. So basically Fubinis theorem, like in this context, is that suppose you have such push forward of the of a constructible function, and when you take the integration on this set, it's the same as you take the integration on this. If you have a constructible function over here, and and then so before you were like taking the integration of this character function, and then you push it forward, and so like I think you were right. That's basically what they say is that you can tropicalize it and subdivide it, like using tropicalization to define some character, like the some Euler characteristic functions that gives like that integration. It's the same. Okay, go back to my note. So I am gonna like, so this is so I'm gonna like tell you for the like the Schön like varieties, and this will simply like this can be proved by the decomposition that I told you. That's right, like write it as the disjoint union of the different pieces, and since that different pieces help us to define the like this Euler characteristic. And so that will be the case that is easy to prove. And then next I will tell you something about like how they generalize it to the general like case.
Right. So
Yes.
So it's like like top
of okay. Let me think. So an example, I'm pretty sure if you are taking like algebraic torus like GM square, and you're taking your x inside here to be simply like the diagonal, it's gonna be like a like a variety, and a non-example is if your x itself is already like not smooth, and like yeah, if it's oh.
Like now I have this map, tropicalization X is
Yeah.
So does it say something about the fiber or the point or
Okay, the way I think about the tropicalization is basically a fixed rate.
yes.
And then that gives you a square current, like a partial square current. And then you act by x that current. And then Schön means, and then as and then this kind of vector is characterized by the fact that the multiplication path, you extend it to all of x. And then Schön means also so particular, by saying that you intersect x with all the boundary strata, that's
Okay, so next I'm gonna talk a little bit about how to generalize the Schön case to the semi-algebraic set case. So first, the definition of the semi-algebraic subset of the torus is again like a finite Boolean combination of nations of the cases where it's x inside T such that there is a function f and a polynomial function f and the polynomial function g such that the valuation of f of x is larger or equals to the valuation of g of x. So the collection of the points such that the valuation of this is larger. And an example of this is, suppose you have a closed-up variety defined by a function like f equals 0. So if your x is defined by x equal like cut out by an equation, and this is a semi-algebraic subset because this set is the same as I say the valuation of f is larger or equals to the valuation of 0. It's the point where valuation of f of x is larger or equals to valuation. And also the same for like all the closed subvarieties. And it's gonna be that. And also another example is that suppose you have the tropicalization map from your T to NQ, and if you have a gamma to be a constructible set, then the inverse image, like the trop gamma, is semi-algebraic. Okay, so we want to generalize this to the general, like the semi-algebraic cases. And the first step is we first look at the case where your x is a closed subvariety, but it's not Schön closed subvariety. So the idea and of the proof is based on a theorem telling you that each closed subvariety can be decomposed as the union, a disjoint union of U1, U2, Un, such that each UI admits an embedding inside some algebraic torus, and it is the Schön embedding. And a second thing is that there is a monomial morphism from Ti prime to T, and it induces a bijection on the k points of on U of k, where Ui of k, where here I mean the k points of this Ui. So yeah, so so for the general case, like the idea is that although this thing is not shown given by the embedding inside T, but we can decompose it into disjoint unions of the varieties, and each of them is actually embedded in some torus, which is a Schön embedding, and this torus admits a map to this T, which induces a bijection on Ui of k. And so this is a Schön closed embedding, which means we have the tropical Fubinis theorem on this part. And we also have the map from Ti prime to T, which is the monomial morphism, which I mentioned like earlier. Like for this, we also have the tropical Fubinis theorem that we can also we have the same definition for the Euler characteristic for this part. And yeah, and then like combining these two together, we get like the case for we get that we have the thing for each of such UI. And yeah, so the UI satisfy that it admits an embedding into some torus such that it is a Schön closed embedding.
So, but they don't have to be closed inside the X or
they don't have to be closed.
Are they
Actually,
semi-algebraic or?
Yeah. Wait, you mean semi-algebraic?
No, what are it?
So the proof they go is actually they do it by induction, and they first show that actually for each X there exists an open affine subvariety.
So they're open.
Yeah, like one of it is open, and then you do induction. Yeah, and then you you take the induction, and then you get like each piece. So yeah, and I think like the proof that they actually shows for each smooth open subvariety that like you can take U to be any like smooth open subvariety, and they can construct a torus embedding into some big torus that is a Schön closed embedding.
So, like, parabolic, like, algebra.
Mm.
Yeah, it's sort of like breaking up.
Yeah. Okay. Yeah, I think that's probably like all the topics that I just want to like go over the idea of how they approach these things, and yeah, and there are like a lot more that I need to learn about the tropicalization, and also the how motivic integration is related to this. So of this theorem, let's think. So you see. But you want a non-trivial example, right? Yeah. I don't think I have an example in my mind.
So
I actually work out a similar example, which is t squared xy t squared y.
Yes.
Yeah,
So
equals
based on
1.
topics of this
Yeah.
is good.
So I think like the tropicalization of this is gonna be, you have -2 over here, and this is gonna be the tropicalization of this. Yeah, exactly. Yeah, because so like if you take this, this is like 2 plus like x. This is like, yeah. So this is the tropicalization of this, and we have I told you we have like a decomposition of this into omega.
Yeah, okay. So we have three internal right? They all have other characteristics. So
They have all have polar character. Okay, let me see. We have this thing. We have, yeah, okay, yeah. I don't know. I have not gone through the example. We're doing it together. Okay. So my like decomposition is gonna, first I have something over here, and I have these 3 rays. So it's gonna be 3 or 4 things. Yeah. And let's see. So over here, the Euler characteristic should be 1. And they're like unbounded, right? So Euler characteristic 0. So yeah. So over here, which means like the piece I need to consider is just this piece, which is the tropicalization, like the inverse image of the tropicalization of this point together with this x. Yeah. And what is the tropicalization of this point inside over here? Like the inverse image of the tropicalization, I believe we can. Okay, I'm gonna do something that's kind of dumb. That is, we can write this in terms of the coordinate as something like t to the -2 plus some higher, or like a, yeah. Yeah, I don't actually.
maybe just write down the definition of this integral for the characteristic.
Oh, yeah, yeah, that's a good idea. Yeah. So let's see. So that's we're taking it over NQ with this this thing, and the part in the middle is the chop this. And so what we are gonna get over here is simply like the volume of trop inverse of this point intersect with x. So this is the thing that we're gonna get, because
I meant like general.
yeah. Oh, okay. Yeah, so this order characteristic is for the whole thing, but this function is the function that we, okay, I erase. This function is the function that assigns you each element inside this NQ with the inverse image of that intersect with x, and the volume of that, right? Yeah. Wait, what does it mean? Like, oh yeah, oh, the theorem says this is the volume of x, right? What is the definition of? Oh, I see what you mean. Okay, yeah. So this is gonna be like a okay, I see what you mean. So this is gonna be like a constructible function on NQ. And yeah, and then it is supposed to give us like a summation over each of the, yeah. Okay, yeah, I'm not sure. Okay, am I It's correctly.
I don't know.
So like how is it with the usual measure? You think like
So what I am yeah, so what I was thinking is that like we can write it as the summation of something like the order characteristic of some like pieces, and together with the trop inverse of that piece intersect with X. So something in terms of this form, but I got a little bit confused of like how we separate it into like you understand what I mean? Yeah. Because this thing, okay, let me, yeah, I think it should be some fundamental, like the, because I told you this assigns to each polyhedron, like, which means, yeah. Yeah, uh-huh. Yeah. I don't actually know. Like, yeah, because it's actually my first time seeing such integral like this. And I was basically like just saying like